Hi everyone, I'm back with a new electronics project, and this one I'm going to call the Infinity Sun Jar. Well, before we get to the infinity part of it, let me explain what just a regular sun jar is. Most people usually take the little dollar store lights, little solar lights for your garden, take the top off of it, and take either like a canning jar or in this case a wire bale jar and just glue it to the inside lid and allow this to have light. Sometimes they'll frost it to help spread the light out a little bit. And I love the idea. There's only one problem with this which I really need to work on, and that's what this project is this right here. This $1 light, it's extremely inefficient. And the reason why is, number one, they're cheap. Where else are you going to get a little solar cell, an LED, and a tiny little battery inside of it for $1? Well, Westinghouse does it, but most places you're not going to find it. The next problem with this is the battery that's inside of here, it's nothing special. It's not a lithium ion, it's none of the newer style batteries, which I can't think off the top of my head. It's the run-of-the-mill 20-year-old technology of an NiCad. And the problem with this is the way they designed the little circuits inside here, which is practically nothing to begin with. You're lucky if you actually get the battery charged all the way. Now, for people who don't remember about NiCads, if you don't charge them up all the way and then discharge them practically all the way, they have a memory effect. Basically, they die at an early age. So the average NiCad lasts about 3, maybe 4 years if you're really good with it. Inside here, you're lucky. Most people will probably attest to this. You're lucky if these last a year or two. And then you got a solar cell. Everything else is good, but the battery's shot. But 9 out of 10 people, what are they going to do? They're going to throw it out and just go buy another one. So now you've just wasted perfectly good components. So the other problem with the garden lights, which if you do the sun jar correctly, is corrosion. These are not sealed very well. So water and moisture does get into them. And if it isn't the battery that goes bad first, it's usually the battery connections or the electrodes or any type of the little tiny circuit board in here gets corroded, built up too much resistance in the circuit, and voila, it doesn't work. So we're going to work on that. Okay, now the way we're going to fix this problem and actually make a very good sun jar so it actually works for years and years to come is, one, of course, act like the other people. We'll fix the one problem real easy. With the corrosion, we'll use a sealed jar. The other problem is entirely in the circuitry for these little cheap $1 units. So we're going to get rid of the circuitry and the battery and just not even keep the LED. We're going to use the even better LED. So basically, we're going to throw this out and redesign our own. And here's the prototype. No batteries at all. And yeah, they're two big capacitors, but they're not regular capacitors. They're actually supercapacitors. Some people, I'm sure, have heard of them, especially if you dabble in electronics a lot. Other people are like, super what? No, supercapacitors, they hold a much bigger charge than the ones you'll see on regular circuit boards. Such as these ones I'm using for testing right now. They're not going to be in the final product and need to be a much higher value, but it's great for bench testing it and getting discharge rates for this circuit. And if we can look right here, these are 2.5 volt 10 farad supercapacitors. So basically there are two parts to this whole system to make it work. One is we're removing the battery and we're going to use the supercapacitors. The other part of it is this little thing right here. And if I can zoom in just enough. There we go. That's one side of it. The other side of it, hopefully you can see that little coil right inside there. Well, this is called a joule thief, and it's basically an unregulated boost controller. And what this does is, this is actually the exact same thing that's in here, it's just, this is actually a lot more efficient. This is about 40% efficient at changing the battery power. This is 80%. But what is it changing it to? Well, inside one of those units, let me see if I can grab one right here. I have open. is a 2/3 AA battery. Here's another one just to compare it to. Actually, maybe about half size. I think they call them 2/3 though, 2/3 AA. Problem with the AA battery is it only has 1.5 volts for an alkaline, one of the throwaway batteries, or 1.2 for a rechargeable. Well, to light a white LED, you need at least 3.3 volts to light it. So I could sit here and connect this all day long. It's never going to light up. It doesn't work that way. So they make what's called a little boost circuit inside there. It's an unregulated boost circuit. That's what I'm saying. This one roughly is about 40% efficient at taking the battery power, boosting it up to 3 volts, and then lighting it up for you at nighttime. This one is a little more easy actually to make and only has, including the LED, 5 components on it total. It's about 80% efficient. You have the LED, you have one resistor on the side, you have in the very center this little black thing right here. It's called a common mode choke. It's basically just a coil with 2 wires wrapped around it in a certain fashion. And the little chiclet looking thing is a 0.1 microfarad capacitor. Put in the correct way, it will actually boost the circuit for you. It oscillates up and down, on and off, and kicks the voltage up to 3 volts. And this way, instead of just hooking up to, say, 2 AA batteries so you get your 3 volts and then throwing a resistor in it so you don't blow the LED, this will actually switch on and off anywhere from 200 to 400,000 times a second. 200 to 400 kilohertz, whatever the transistor can actually handle in there. So what happens is your eye perceives it as constant light, but it actually turns it on and off so many times, you're actually saving power at the same time. That's why this will actually last fairly long. Another very good part about the supercapacitors are, remember I gave you the battery life of the little NiCads that come inside the garden lights? Yeah, they're probably good for most times 1 to 2 years. A few you might actually gotten one out there that lasts 3 or 4. The duty cycle for a once a day charge and discharge on these is roughly 100,000 times. Now, I did the math before, I can't remember immediately what it was, but I think the capacitors have a good chance of outliving us. So, that's another reason why we're going with supercapacitors. Now, there are a few different things you have to think about when we're going from the battery chemistry and charge and discharge of a rechargeable battery to a supercapacitor. When a battery discharges, you start at 1.2 volts. This circuit usually will shut off at about 0.9 volts. At that point, the battery is considered dead. There's nothing more you can do with it besides recharge it back up to 1.2 volts. So you're only talking about a 0.3 volt difference for the whole charge in this battery. Supercapacitors, on the other hand, are a little different. They don't charge discharge like a NiCad, a little bit down and then all of a sudden drop down. That's a NiCad. It's a very non-linear discharge curve. Supercapacitors, on the other hand, what they do, charge them up to 2.5 volts complete, and they will discharge at a very linear rate. So we can't just take this, throw a supercapacitor in there instead of a battery, and expect it to work for very long, because it's going to shut itself off at 0.9 volts, and the circuit's not made to handle 2.5 to begin with. So that's where our little Joule thief friend comes in. I've already tested it, and it actually works very, very good at 2.5 volts. I have these charged at 2.5 volts right now. So let me plug this in. You can see it gets very, very bright compared to that. So there's a very big difference here. Best thing is too, this Joule thief, it will actually discharge the supercapacitors all the way down to actually 0.5 volts, and it will stop making any usable light. Now the other thing is we have to have 2 parts of this circuit for it to work. One is the Joule Thief itself to make the light. The other part is a charging and on-off circuit. Now in that circuit, I lose zero point 0.1 volts, so the Joule Thief will shut off at 0.6 volts. So we're using from 0.6 all the way up to 2.5, so we want to use as much power as we can from the supercapacitor. Now, to show that this is actually even more efficient, this will run for an hour and a half before it shuts off on only 20 farads of power. That's the equivalency of having this battery sitting at like 0.94 or so. So these are actually very efficient, and I'm going to go switch over right now to a quick video I made. I did a discharge test of this. Charge capacitors all the way up to 2.5 volts, set a timer, set a voltmeter, so this way you can see how bright the LED is as it slowly discharges and the time it took to discharge 20 farads worth of power down to 0.6 volts. Okay, we're going to do a duration test now, and we're going to charge up to 2.5 volts with two AA batteries. We'll have the clock running in the background, so we see how long 20 farads of capacitance will last with this Joule Thief. So let's give me a second to charge it up here. We're going to overcharge it just slightly. It's still not quite 2.5. Okay, as soon as it hits 2.5 even, we'll start the clock. Now you can see in the video what happened was the Joule Thief actually illuminated the LED for an hour and a half. There was usable light, what I would consider that you can actually see around with or use as a flashlight, or actually see it coming out of the jar for roughly an hour or so. I'd say an hour, hour and 5 minutes. After that, it does put out light, but it's very minute at that point. You might not be able to tell as much from the camera recording. Now after, say about, I think it was 1 hour and 31 minutes, it kept recording for a little bit longer, and the camera actually did pick up light. That's actually infrared light. I could not see any light itself, so apparently this LED, when it gets very, very low power, only emits infrared light. It's not enough juice into the LED to make a visible light that the human eye can see. Okay, now I just want to give you a quick showing of the schematic that I made on my computer using a program called KiCad for Linux. And here you go. Now you can see on the left side of the circuit is the charging, the supercapacitor, and the on-off circuit. And the little part over to the right is actually the Joule Thief. When this project is all done and over, I will post this in a file format so this way everyone can download it. You are free to copy this, give any comments that might be able to help me design this some more. But from what I've seen, these values and this setup partially from the supercapacitor, or the super jewel thief is copied off from Make Magazine's solar jewelry, and I'll show a link for that down in the description. Now the other half of it, the charging and the on-off circuit, is an adaptation from a person online, goes by the name of Lid Motor. I don't have a link for him, but he originally designed the circuit. If you search YouTube for Lid Motor, LIDMOTOR, you'll find him. I believe he made a few circuits. He's posted them on YouTube. He has a couple little guys that he affectionately calls Huey, Dewey, and Louie. So go ahead and check out his videos, but he's the one I originally got the on-off and the charging schematic from. Now, to take this from an alpha stage, from the breadboard to the beta stage, which is going to be my first ever printed circuit board, and to order it, I've almost got the design done, but I'm not ready to order yet. I'm waiting for two parts to come in first. I'm waiting for a bigger solar cell, because this is one of the solar cells that came out of one of these. The open circuit voltage on this is only 2.1 volts, and even without the diode in there to keep it from discharging the supercapacitor at night, it's not going to charge the supercapacitor up, and we're not going to get the efficiency of the circuit that we want. We want to get that supercapacitor charged all the way up to 2.5. So I got a bigger solar module on order. It should be in the mail in the next few days. And also, we want this circuit to run for a minimum of 8 hours. And for that to happen, after watching the discharge video that I showed you, we would need roughly 160 to 180 farad supercapacitor for this to work. Well, I want to go a little bit further than that, and actually I got a very good deal. I'm not going to say where yet, but I got a very good deal on 350 farad 2.7 volt supercapacitors. I ordered one for a prototype, so this way I can hook it into the breadboard with the bigger solar module, and this way I can test it a little bit and see if I have to play with the diode on the solar panel, or I have to change the circuit around a little bit more for this to work correctly. This way we get the actual amount of time we want out of the supercapacitor. But I'm hoping, since this one's rated for 350, we should easily break the 12-hour mark of a constantly running nice bright LED from our Jewel Thief, and possibly even further. And at the same time, hopefully the solar module is sized correctly, so this way it will charge on a full sunny day. I'm hoping it will be charged within 4 hours, because that's another good thing I forgot to tell you. When you charge a supercapacitor from a solar panel, it takes the charge a lot faster than a little NiCad battery. And the reason being is the resistance. Everything has an internal resistance. Inside a NiCad battery, it's actually pretty high. So the solar panel has to do a lot of work to get that energy into a battery. Supercapacitor, on the other hand, the internal resistance of it is minuscule. So it has to do no work practically. It just feeds it power and it just sucks it up. So even though we're going from little tiny ones to a 350 farad supercapacitor that's roughly going to be the size of a C-cell battery, maybe actually a little bit between a C and a D. It's not quite a D-sized battery. It will take the charge very quickly. So I'm hoping it will charge in full sun in 4 hours, or on an overcast or slightly cloudy day within 8 hours, and we'll still get at least a minimum of a 12-hour run, which is perfect for if you leave your lights on all year round. These kind of die in the wintertime, in the snow, or the short daylight that you have. My Infinity Solar Jar, hopefully once I get it all built together, these things, it doesn't matter if it's 20 degrees below zero and 5 or 4 hours worth of sunlight a day. Should keep on working no matter what. So do me a favor, subscribe to my channel, and I'll keep you updated with what's going on with this.